Today's lesson is going to be investigating the relationship between the DFT and the DTFT. We're going to start off with a fairly comprehensive review of what we discussed last class about what the relationship is between the DFT and the DTFT. Remember the DFT, finite sequence, same length of sequence as our input x of n, as opposed to the DTFT, which is a continuous frequency function. And we go from this continuous frequency function of the DTFT to the finite length sequence, the DFT, just by sampling it. We'll talk about how to go in reverse. So if you sample the DTFT to get the DFT, we will talk today about how to go from the sampled signal into the continuous frequency signal, which at first seems impossible since there's a finite number of samples in the DFT and an infinite number of samples in our continuous frequency DTFT. But it turns out to be not very complicated. And then we'll talk about the relationship between the indices of the DFT, which it's indexed against k, an integer, versus omega, which is how we index the DTFT, versus our continuous time frequency back in the continuous time world. So this is of critical importance because this is really why we teach digital signal processing, because we sample a continuous time process and we take its DFT because it's easy to compute, and we find some sort of spike in signal energy at k equals 136. Then we want to know what continuous time frequency does that correspond to. But before we get into all these details, let's begin with that review. So last class, we said that if we're given a discrete time signal, which is of length n, meaning that n equals 0, 1, 2, blah, 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 all up to capital N minus 1, then it will have n samples. In that case, it's DFT, which we write as capital X of k. I'm showing that it's a capital X by the little lines up on the top and bottom that I give it, and k is an integer. It's just n samples of the DTFT. Remember, the DTFT is x of e to the j omega, where omega is continuous. And that's we're taking these samples of the DFT between 0 and just barely under 2 pi, such that if we had one more sample, it would be at 2 pi. It's exactly n minus 1 over capital N, 2 pi. So as n gets to be really big, you can see this goes to 1, and we really are going to almost exactly 2 pi. So in other words, we're going to sample the DTFT at every omega equals 2 pi over capital N times k, for k equals 0, 1, 2, all the way up to n minus 1. Just like our n value in the time domain, they're the same length, the DFT and the time domain waveform. So let me give a quick example. Maybe it's not going to be that quick, but let me give an example that'll show how this works and show how this seemingly simple concept actually gets very complicated in a hurry. So here's a simple signal. It's in the time domain, and we call this a pulse. Sometimes you'll also hear it referred to as a top hat. I'll call it a pulse. It's something that's 0 everywhere except for a finite number of places where it's equal to 1. And to make it simple, I'll make this a capital N equals 10 length sequence. So it's ones between 0 and index of 9. So we want to find out what its frequency content is. And to find its frequency content, intuitively, we want to find its DTFT first. Now, the DTFT, you might remember, we covered this in an earlier class. It's a sink. And the sink is sine of x, whatever x is, maybe it's n in the time domain, or maybe it's omega in the frequency domain, divided by x. Now, there might be extra constants like a k1 or a k2, but the point is still that it's a sine of x over x. It oscillates between positive and negative numbers, and it has an envelope that goes down. Let me draw the pieces of it. So here's sine of x. And then if we want to draw what 1 over x is, this is what 1 over x is. It quickly goes to infinity. And we're going to multiply our sine of x by our 1 over x. So what happens when we multiply this orange by this cyan color? Well, it's pretty clear for most of the graph what it looks like. It's going to look, we're graphing its frequency domain behavior here. For large values, it's going to have this sort of sloping down character since it's divided by x. So for large values, it might look like something that goes eventually down to 0. Now, of course, since we're in the discrete time domain, it's going to go like this only until about pi. And then for values bigger than pi, it's going to start to grow again. But what is it doing over here for low values? To evaluate at 0, we'll end up getting sine of 0 over 0, which is 0 over 0, which is indeterminate. So we just need to figure out what is that limit as x goes to 0 of sine of x over x. And it turns out that for small values of sine of x, it's pretty much equal to x. You can try that out on your calculator by taking the sine in radian mode of 0.01, and it will return 0.01 or something very close. So for small x, sine of x is about equal to x. Therefore, as our limit goes to 0, we get just x over x, which is 1. And so our whole value, our whole DTFT looks like this. And obviously then it's got to go up to 1 over here at 2 pi. So this is its DTFT. And then we're going to sample it to create the DFT. And if we do this correctly, if it had one more sample, it'll be here. And the question is, where are we sampling in between? It's even between 0 and n minus 1, which would be 9. We need to have 9 more samples in here. But I just drew this freehand. I don't know exactly where these zeros are, so I'm not sure exactly how to draw the DFT. I'm going to use MATLAB for that. So let's switch over to MATLAB. So firstly, how do we create our signal? We could create our signal by putting 10 ones in here, but I'll probably miscount it. So instead, I'm going to use the command ones. We have 1 row. We have 10 columns in our vector. So that's our row. That's our x. And I'm going to compute its DTFT. Now, there is not a built-in command in MATLAB to do this. You will create your own command, DTFT, in one of our labs. But for now, I'm going to build it for you. The DTFT that I programmed in takes an omega vector. So we're going to program that to compute it between 0 and 2 pi. And I'll have it compute a bunch of values to make it nice and smooth. And then I'll have it graph the results. This initial 0 just says that my original time domain waveform starts off at n equals 0. And this is the result. So here's the magnitude, and here's the angle. It has an angle because our original waveform began at 0. If I had it evenly distributed between -5 and +5, then it would have no angle. But this does have an angle. It has non-zero phase. What I'm most concerned about is the magnitude here, though. So this magnitude, firstly, it doesn't quite look like what I graphed before. It's always positive, but that's because I'm graphing its magnitude. So this is actually flipped. The real part would be flipped underneath here. So we would see that sine wave going back and forth. and it indeed is mirrored around pi. The x-axis here, I've written in terms of normalized units. So when it says 1, it means 1 times pi. So here it is between 0 and 2 times pi, and it is even around our 1. It's symmetric around our 1, around our pi value. Something else to realize is that because this is a low frequency signal, it's mostly ones, you'd expect to see most of the signal energy concentrated at low frequencies. But because where we're not drawing the signal, the assumption is that it's zeros, there is a transition then. It's 0, 0, 0 until we get to n equals 0, and then it bumps up to ones, and then at n equals 10, it bumps back down to zeros again. So it has some changing, some high frequency energy, and that's what's shown over here. That's why we get this sync value. Let's see what its DFT looks like. So capital X is its DFT, which we compute using the FFT algorithm in MATLAB. And now I'm going to plot the absolute value of that down here. Oh, I shouldn't have plotted it. I should have stemmed it because it's a discrete data. It's kind of hard to see. I'm going to stem it, but I'm going to use a thicker line width so we can see what's going on. Uh-oh. This doesn't look anything like that, does it? Or does it? So actually it is. What's going on here is that, remember, it goes to just under 2 pi. So these things aren't supposed to align correctly. If there was one more data sample over here, it would align. Instead, what it is 10 evenly taken data samples from up here. And watch this. If we took one here, plus another one here at this bottom, so it's 1, 2, 3 samples, 4, 5, 6, 7, 8, 9, 10. Everything except for the first sample is 0, and that's what we see down here. So this is a perfect example about why the DFT can be really misleading to people who don't know much about it, because it can sample that DTFT up here at odd places, and you lose information. Fawaz pointed out that it's like frequency domain aliasing of your signal. How can we better sample the DTFT with the DFT? And a few lessons ago, Jeremiah said you could zero pad it. So let's do that. Let's create a new signal, X1. And I'm going to take that original signal X, and I'm going to just zero pad it a little bit. And now I'm going to graph that. Its DTFT doesn't change at all, just like it shouldn't, because we just added zeros to it. But watch what does change. Its FFT now is going to be far more finely sampled. So when we stem that, all of a sudden, not all zeros. Now we're sampling it off the high peaks a little bit, and we're seeing some of this underlying signal, this bouncy signal. Now, the bouncy sync. Now, if we wanted to sample it still more finely, we would just zero pad it more. So instead of zero padding with 4 zeros, let's zero pad it with 100 zeros. Now, once again, I'm going to plot the DTFT of it. And once again, the DTFT, not changed at all, as it shouldn't. But that DFT, now that DFT really nicely samples the DTFT before. Now you can see it really does sample it almost up perfectly to that 2 pi. Of course, notice that the index is completely different. It's not between 0 and 2 pi. It can't be. The DFT has a integer index. The indices are 0 and 1 and 2 and 3 and 4, all the way up to, starting from 0, all the way up to a maximum of 1 less than the length of the signal, so that in the time domain. And I don't remember how many signals we had, but I think we had 10 zeros and 100 ones. So there's a total of 110 samples here on the DFT between 0 and 109. Something else I want you to notice. Since the DFT is a sample DTFT, and let me draw a typical DTFT for maybe it's a low pass filter. So it'll look something like this, between 0 and pi. And of course, we're plotting the DTFT with respect to the continuous variable omega. Remember that DTFT is a sampled. The DFT is a sampled DTFT. And it's sampled up to just before the omega of the DTFT would be 2 pi. So we can extend that up here. Oh, that's pretty poor. Let me try that again. That's better. All right. So we want to sample it to just 1 under 2 pi. Realize that because of the way we're doing this, when we sample it here and say we're sampling it at these points, we have a underlying n here of 1, 2, 3, 4, 5, 6. So we're sampling it evenly so that if we had one more 7th sample, it would be right at 2 pi. Realize that because of the way we're doing this, there are certain symmetries present in our signal. This, the right side and the left side, are complex conjugates. And when they're complex conjugates, it means that the magnitudes are the same and the real part is the same. And it means that the angles, the phase angles, are opposite signs and the imaginary parts are opposite signs. But because of that, it means that these 2 points have to be complex conjugates of each other. And these 2 points have to be complex conjugates of each other. Of course, this one's left out alone. And that's with our n equals 6. If we had n equals 5 to make it an odd number, now we have 1, 2, 3, 4, 5 evenly spread. And now the complex conjugates are a little bit different, right? Now we have these guys as being complex conjugates, but this point at pi didn't quite draw that perfectly there. Let me try that again. This middle point that's at pi isn't sampled. So over here, when n is even, we do sample right at pi. We have a particular sample in the DFT and our x of k here. So this is 0, 1, 2, 3, 4, 5. This is 0, 1, 2, 3, 4, since it's an n equals 5 length. So in this, for a odd, we never quite sample it at the highest frequency. There is no index k, which corresponds to its highest frequency. But instead, we have these groups at 2 and 3, which will be complex conjugates, and 1 and 4, which will be complex conjugates. So if I was to write that in math, I would say x of 1 is the same thing as the complex conjugate of x of 4. And when n is even, we do sample the highest frequency. These will be complex conjugates. These will be complex conjugates. And I can say again, for this example, that x of 2 is going to be equal to the complex conjugate, as an example, of x of 4. So the magnitudes will be the same and the phases will be opposite. The real parts will be the same. The imaginary parts will be opposite. And since there is no complex conjugate for this value and this value, it means that both of those values have to be real numbers if n is 6. Whereas for n is odd, the only samples of the DFT that are guaranteed to be real is for k equals 0.